Okay, let's get started. So, in the last time we have learned about the likelihood ratio test, and we can see that the usual z-test and t-test can be derived from the likelihood ratio test. So, uh, so in the hypothesis testing, the key idea is we would like to um, see. We would like to have a good test. So here, the good test means we would like to mi minimize type to error as small as possible when we have control on the type 1 error. So that we can have the large power. So when the null hypothesis is the false. Here we like to have large probability for rejecting the null hypothesis when null hypothesis is false, and so that probability that reject H0 when H0 is false is greater or equal to the probability that we reject H0 when H0 is true. So that test is called an unbiased test. So if a test satisfies this following inequality, so inequality is probability that we reject H0 when H0 is false is greater or equal to probability that we reject H0 when H0 is true. So you can see that the probability in the left hand side is probability for the correct decision, and then inequality in the right hand side is the probability of making incorrect decision. Actually, the right hand side, the probability is that the type 1 error, the probability of type 1 error. So we said the test is unbiased when we our probability of rejecting H0 when H0 is false is greater or equal to probability of rejecting H0 when H0 is true. And equivalently, the test is unbiased if So we have a power function, and the power function under the alternative power hypothesis is greater or equal to power function under the null hypothesis. Then we say the test is unbiased. So let me give an example for this one. So let's say we have a binomial phi and probability beta, and we consider testing H0. Theta is less than or equal to 1/2 versus the alternative hypothesis theta is greater than 1/2. And then the testing procedure is to reject null hypothesis if x is equal to 5. And we want to show that the test is unbiased. So here, our power function is since we reject the null hypothesis when x is equal to 5, so the power function is the probability that x is equal to 5, and then by calculation this is set up power fifth. Then clearly, the power function under the alternative hypothesis is greater with the power function under the null hypothesis. So the range of theta under the null is the less than or equal to 1/2, and range under the alternative is the probability is greater than 1/2 and less than 1. So the power function under the null hypothesis always greater less than or equal to power function under the alternative hypothesis in this case, because theta power fifth is an increasing function on theta, which means that if theta value increases, the theta over fifth is also increasing. So if theta is greater and greater, then theta fifth is also greater and greater. So clearly the power function under the alternative hypothesis is greater or equal to power function under null hypothesis. So this test is unbiased. Now we have an unbiased test, which is comparing under the null and under the alternative. Now we would like to consider a class of tests has the most largest power function under the alternative hypothesis. So we would like to pick up the best test, which gives the smallest type 2 error among the many tests. So that test is called the uniformly most powerful test. So we have a class of tests. I will denote as C for no theta is belong to omega 0, and the alternative is theta is belong to omega 0 complement. And the test in the class C with power function beta theta is uniformly most powerful UMP in class C if the power function under the theta is greater or equal to power function under theta prime. For every theta belongs to the alternative hypothesis, and beta theta prime is the another power function of the another test in C. So if the power function is greater or equal to in the one test is greater or equal to the power function in another test, for every theta in the alternative hypothesis, then we said the test is the UMP in the class C. And then continuing this definition, if we consider C is equal to all level alpha tests, if we consider the all level alpha test, the UMP test in this class called UMP alpha test. And then it is the best in class C or the most powerful level alpha test. So UMP alpha test is the best test among all class of all level alpha tests. Then how can you find this UMP alpha test? So first we would like to consider the simple hypothesis, which is the theta 0, H0 is the theta equal to theta 0 and versus and H1 is theta equal to theta 1. So null and alternative hypothesis is the based on individual value of theta. And then for simple hypothesis, the UMP level alpha test always exists. So now I'm going to talk about the important lemma, which is called the Neyman-Pierce lemma, which is the basis for finding the UMP alpha test for simple hypothesis. So we are considering testing the simple hypothesis. So consider testing H0 is theta equal to theta 0 versus the H1 is theta equal to theta 1, and we have corresponding PDF or PMF. And then if we have two conditions, the first condition is that if X belongs to the rejection region, the X belongs to rejection region, if PDF or PMF value under the alternative hypothesis is greater than K times PDF or PMF under the null hypothesis, and X belongs to the complement of rejection region, which is acceptance region, if PDF or PMF under the alternative is less than K times F and the PDF or PMF under the null hypothesis. So actually these two conditions are very important. So if we, for some case greater than or equal to 0, then we have the condition for belonging, rejection or acceptance region, and we have a second condition that the alpha is the probability that the sample belongs to the rejection region. So this is the two important conditions. Then for sufficiency, so which means that if we have tests that satisfy the first and second condition, that's the UMP alpha test. And also the reverse also holds, which means that so if there is a test satisfying 1 and 2 with k is greater than 0, then every UMP alpha test is the size alpha test, which means that it satisfies the condition 2. And then so every UMP level alpha test satisfies number 1. And then if you have UMP level alpha test, it satisfies the first condition, which is that if the ratio of PDF for PMF under condition alternative and divided by the PDF for PMF under the null is greater than the K, where the K is greater than 0. If then it belongs to the X, the sample belongs to rejection region, that condition, and also for reverse inequality for ratio of two PDF for PMFs, then it satisfies the X sample belongs to the acceptance region. That condition is satisfied with except the set A, where the probability that X belongs to the set A, sample X belongs to set A under the null, and alternative is the 0. So we are not thinking about the set A, which is the set A that the probability under the theta 0 and theta 1 belongs, the X belongs to set A is equal to 0. So we don't consider this. If we remove this set A, then every UMP level alpha test satisfy the first condition. So if we have UMP level alpha condition, what this necessarily means that if we have UMP level alpha test, then it satisfies the condition 1 and condition 2. So the proof is in the textbook, so I will not go through here. So for proof, please look at the textbook.